particularly gratifying to me to receive an award honoring the monumental contributions that Will Allis made to gaseous ionized physics, because I had the great privilege of knowing Will Allis for at least 35 years now. I first met Will Allis, it must have been about 1960, 1959, when I was a fledgling associate professor of physics at the University of Texas, and he visited there. Professor Allis maintained an interest in our research and was a source of helpful interaction. Our research in Boulder for many years. In addition to his scientific inspiration, I fondly remember such occasions as hikes in the mountains near Boulder and a particularly memorable canoe trip in Wyoming, where his wonderful qualities as a person were manifest. He personifies for me the ideal of a scientist, humanist, scholar, and remains a lifelong inspiration. I'm going to use this occasion to reminisce about the early days of the glowing afterglow development, using a few somewhat random discoveries or findings from the early days that I hope were of sort of general interest still this much later. In 1962, I joined the National Bureau of Standards in Boulder, the Upper Atmosphere and Space Physics Division of NBS, being largely somewhat frustrated by a 9-hour teaching load at Texas. I think was the prime motivation then. I was aided in this move by a very good friend, the late Herb Broida, who was one of the 2 senior scientists at NBS at that time, Hugo Fano being the other. Both Herb and Hugo were strong supporters of our program in NBS Boulder in those early years. I had the opportunity to develop a laboratory program to further the understanding of ionospheric physics, which was one of the missions of NBS at that time in their concern with radio propagation. I had the extremely good fortune to be accompanied by my first 2 PhD students from Texas, Art Schmeltcup and Fred Faisenfeld, whose input into the development of the flowing afterglow was absolutely essential and critical. And both are currently world leaders in other aspects of atmospheric science today. The ionosphere, is to say, concentration or distribution of charged free electrons in the atmosphere, was discovered about the turn of the century when Marconi transmitted radio waves from England to the United States. And since radio waves presumably propagate along straight lines, there seemed to be a problem here, which was resolved by Pinelli in America and Oliver Heaviside independently in England in 1902, where they proposed that there was a reflector, namely free electrons, for our ionosphere. The electron distribution itself was measured very early by radio reflection techniques, but the distribution of ions was only determined after the Second World War with the development of rocket technology, which allowed the flight of mass spectrometers. This early distribution of Charlie Johnson from NRL, very near us, in fact, I can see NRL from my hotel window here, showed what the ions were, what the ion composition was. So the question was to explain why the ion composition is as it was found to be. I'm standing in a bad spot. For example, it's clear that the ion O plus is a primary ion produced simply by the... Towards me a little bit. Am I standing in in a good spot now? So help me, I won't move. I'll sit on the floor. So the O plus is obvious. It's a primary ion produced by the photoionization of the major neutral in the atmosphere at these high altitudes, atomic oxygen. The NO plus is obviously not a primary ion. It could be produced by the reaction of O plus with N2, or it could be produced by the reaction of N2 plus with atomic oxygen. In fact, it's produced by both. And the question is to quantify these questions with measured rate constants and finding out just what the processes were. In a similar way, the O2 plus is produced by charge transfer of O plus with O2. The piece of this puzzle that we chose to address was to determine in the laboratory what the reaction rate constants for ion-neutral reactions were and measure them quantitatively. And surprisingly enough, in 1962, there were no firmly established values for reaction rate constants for ionospheric ion molecule reactions. That may be less surprising to some of the younger people who probably suspect that there wasn't anything known in 1962. That's the way it was. Here is a photograph of an early glowing afterglow system. It's not the very first one, it was the second one. This is a hollow cathode discharge. Here's a cathode and an anode. There's a very large Roots blower pump exhausting gas down here at about 10 to the 4 centimeters per second at roughly a half a torr pressure. And we call this was inspired by a similar experiment that Herb Reuter had at Bureau of Standards in Washington, where he simply used this as a spectroscopic light source. Well, just at about this time, Bates, Kingston, and Porter invented collisional radiated recombination, a process of 2 electrons and a positive ion recombining into excited states, and that gives rise to the light emission. There's a very rich molecular, helium molecular, and helium atomic spectral emission from this afterglow. We call it afterglow because previous attempts to measure ion molecule reactions had been done in a stationary afterglow. Fixed volume of gas, you break it down with a discharge, and then you attempt to follow the ion composition in time, and from that deduce ion molecule reaction rates. And probably not many of you in this room will be surprised or have any difficulty in understanding why that was not successful. One of the earliest discoveries of physical interest that we made from this experiment was that there was no dissociative recombination of the helium molecular ions. That was the first molecular ion shown not to have a fast dissociative recombination. That is, capturing an electron and splitting into 2 atoms. And may still be the only one. I'm not entirely sure of that. And it was very easy for us to show that. Looking at the atomic emission lines in that afterglow, we were able to add neon into that afterglow. Neon destroys the molecular helium ions, essentially every collision. The intensity of none of the atomic lines changed a bit. So the atomic emission lines were coming from recombination with atomic ions, and the extensive molecular spectra was coming from recombination of electrons with the molecular ions. And of course, the fact that we saw a very extensive molecular spectra was pretty much a clue that the electrons were recombining into excited states and not dissociating the Ag2+. Well, it happened at about that time that Professor Mulliken was visiting in Boulder, and he, in fact, was staying at my house. We had a previous association on a completely unrelated problem, and so I was walking him through the lab and telling him about things which I didn't think he might have any particular interest in, but he was there. By the time, and I mentioned this result, that the He2 plus did not have fast dissociative recombination, by the time he got back to Chicago, he called me in after about 2 hour and a half phone conversations. He was ready to write a paper on what was going on here. And it had some very interesting implications because in his what he realized is that there must not be curve crossings between the He2 plus potential curve and repulsive neutral He2 excited state curves, otherwise one would have the dissociative recombination. And his classic 1932 Reviews of Modern Physics paper, where he gave extensive molecular potential curves for He2, he had simply a lot of stable excited state curves and a lot of simple repulsive curves. One result of this was he was violating the non-crossing rule. But as he says in his later Phys Red paper, in 1932, that seemed the easiest way around that problem, and so he did that. Well, when he realized that there were not such crossings from this result, they went back and they started putting in large cones in these repulsive curves, which avoided the crossings and which salvaged the non-crossing rule. And so that was that result. The first ion chemistry result that we got out of this was essentially the day we turned it on. This first tube that was actually put together with rubber O-rings and things like that, and you might not be surprised to know that there were air leaks. And in fact, if you had a good spectroscopic eye, you could see the blue tint from nitrogen in here. And if you didn't, you could take a little handheld spectroscope and you could look up at the light source and you could see the first negative system of N2 plus. We had an air leak. Since we knew there were ions here, we added a mass spectrometer down at the end in order to do ion chemistry. That was our contribution to this field. And in the ion mass spectrometer, little quadrupole, which we built at that time because in 1962 they weren't commercially available, we saw about 5 times as much N plus as O plus, so we knew immediately that helium ions reacted more rapidly with nitrogen than with oxygen. And that gave a result concerning the escape of helium from the Earth's atmosphere, which had just turned up at that time. And the problem is the following. Neutral helium is produced into the atmosphere at the rate of about 10 to the 6 atoms per square centimeter per second from the decay of uranium and thorium in the crust. And the question then is, how do you get a balance here? The Jeans escape or thermal escape is far too low for this. Putting the problem another way, you could produce the helium in the atmosphere, about 1 million atoms per square centimeter per second around it, in about 1 million years, and presumably the system had been running a few billion years, or perhaps it wasn't a steady state. But at about this time, well, in 1961, Marcel Nicolay deduced that there was a lot more helium in the atmosphere, in the high atmosphere, 400 or 500 kilometers, than people had thought, which he called the heliosphere. He deduced that from looking at the orbital decay of the Echo 1 satellite, which I think was a huge balloon. And the friction was such that it slowed down more rapidly than one would think expected. And from that he deduced a heliosphere, a certain distribution of helium. And then he calculated that the rate of ionization of helium from that much neutral helium would be about 1 million ions per square centimeter per second. Well, Bates and Patterson, noticing the coincidence of those numbers, argued that if every time a helium was ionized, it would escape from the atmosphere. That would give the balance. And they proposed that the way that could happen is that if helium ions react with oxygen, give O plus, a process in a fast helium, process which is 6.2 volts exothermic, and the escape energy of helium from the planet is only 2.4 volts. the light helium might, if the mechanism is right, get most of the kinetic energy. That would provide the balance. But of course, that required that helium ions not react with nitrogen, because there's a lot more nitrogen 400 or 500 kilometers than oxygen, because oxygen is easily photodissociated. Well, as soon as we saw that helium ions reacted more rapidly with nitrogen than oxygen, of course, that threw out that hypothesis or theory. And so we, with some enthusiasm, conveyed that result to the editor of Planetary and Space Science, Sir David Bates, who we knew had a prime interest in that. David Bates was one of the great atomic molecular theorists of our time, as well as being a dominant figure in astronomy. It was my good fortune to have had a steady interaction with him during the early days and lots of encouragement and inspiration. It was a very great pleasure for me a few months ago to receive a letter from David Bates congratulating me on receiving this prize. And it was a very profoundly sad occasion a few days later to have a call from Ray Flannery telling me that he had passed away. Well, in order to do ion molecule reactions, we did the fairly obvious thing of adding into this flowing afterglow various gases. There's a reaction port here, one you can sort of see here. So, for example, if we wanted to do O+ reactions, into this helium afterglow, we would add oxygen, and then we would rapidly add O+ ions, also O2+ ions from the pinning ionization. Coming down to our mass spectrometer, if we wanted to study the reaction of nitrogen, we would add nitrogen. The rate of disappearance of the O+ as a function of nitrogen added then would give a quantitative reaction rate constant. We knew the reaction time from the velocity and distance. O+ plus N2 is a good example because that is the most important reaction in the ionosphere, as I will show shortly. It controls the electron loss in our ionosphere. We could add CO2 and study the reaction of O+ with CO2, which would be the rate controlling step for electron loss in Mars and Venus atmospheres. Turns out the reaction of CO2 is 1,000 times faster, so those planets have relatively less dense ionospheres. Here is the summary of the situation. The F region maximum around 250 to 300 kilometers, where the electron density is the maximum around 1 million ions per cc. The ionization is photoionization of O, and the loss, because radiated recombination to atomic ions is essentially negligibly slow, the rate controlling step for loss is conversion of the atomic ion to a molecular ion, where the recombination rate is maybe 5 orders of magnitude greater. We added some temperature control to this flowing afterglow, and we were able to measure reactions up to about 900 degrees K, which is a terrible job. You get all kinds of material problems at 900 degrees K, and that was not very successful and very painful, but we did get some results. Here's our relatively slow O+ plus N2 reaction. These are the reactions, in fact, the ones right down here, these bottom 4, that control largely the chemistry of the F region of the ionosphere, where the electron density is greatest. The only one we were not able to measure temperature dependence of was the reaction of N2 plus O, because there was incompatibility between the plumbing involved in heating this tube and to get in O atoms or N atoms. But reactions which are very rapid, we observe right away, essentially have no temperature dependence, so that's not much of an uncertainty. And reactions which are slow decrease invariably for ion molecule reactions. We did another interesting thing with the O+ plus N2 reaction, which is to measure it as a function of vibrational temperature. That was a first ion molecule reaction measured as a function of the vibrational temperature of the neutral, and I think may be the only one still. This is of more than academic interest. Temperatures as high as 6,000 degrees have been observed in auroras, for example. And it turned out there were a number of people interested, since this controls electron loss and can increase by, say, a factor of 40. There were a number of people who were concerned with electron densities under severely disturbed conditions in the atmosphere for purpose of communication, whose interests were not, I think, largely with auroras, but who utilized this kind of information. And a modern glow and afterglow system looks something like this. On the metal tubes, we put in a region where we can apply an electric field so that we could increase the relative kinetic energy of the ion and neutral up to several volts, depending on the kinematics. So you get kinetic energy dependencies, which is a lot easier than getting temperature dependencies, and of course covers a much wider range. Another advance that was made is the selected ion feature. Nigel Adams, one of our early postdocs, and David Smith in Birmingham, England, introduced that, where you can introduce an individual ion mass spectrometrically from a low pressure discharge to the high pressure flowing afterglow, high pressure being the door or something like that, by an aspirator arrangement. And that simplifies life a lot, where you don't have a lot of possible ions involved. The